In this video, we look at chapter 3.2, where we are using elementary row operations to calculate a determinant. So our learning objectives for this video are to learn how to use elementary row operations to evaluate a determinant, use elementary column operations to evaluate a determinant, and then recognize the conditions that yield zero determinants. So in practice, we rarely evaluate determinants using expansion by cofactors, what we saw back in section 3.1. So the properties of determinants under elementary operations provide a much quicker way to evaluate determinants. The big idea here is that we know we can rearrange matrices using row operations, and by using those elementary row operations, we can get matrices in a form where we have zeros, and that makes calculating the determinant by hand much quicker. So we are going to see the properties that apply that we can use with elementary row operations, and then we will see an example of how we can actually rearrange a matrix. Of course, you can also use technology to calculate determinants. So this gives you some sense of what you would do if you were trying to code technology using programming to try to create a program that finds determinants, and an underlying sense of how computation works. So I'm going to go through some of our theorems here a little out of order. So theorem 3.9 tells us that the determinant of A transposed equals the determinant of A. So we're going to come back and see that proof in section 3.4 next week. So for now, we will take this as a property that we can use, and then we'll see why it's true down the line. So theorems 3.3 and 3.4 are related to the elementary row and column operations that we can use for determinants, and how we can get conditions that yield a zero determinant. So we are going to prove these theorems in conjunction in this section. So theorem 3.3 says let A and B be n by n square matrices. And so there are three parts to this, parts A, B, C. Part A says when B is obtained from A by swapping two rows or two columns of A, then the determinant of B equals negative determinant of A. Part B says when B is obtained from A by adding a multiple of one row of A to another row of A, or one column of A to another column of A, then the determinant of B equals the determinant of A. All right, so we see if there's a row swap, we get a sign change. If we add multiples, the determinants are still equal. And that makes sense because if you think about adding the multiples, multiplying through and dividing, you're not going to get a net change. All right, part C of theorem 3.3. When B is obtained from A by multiplying of a row or column of A by a non-zero constant C, the determinant of B equals C times the determinant of A. So what we're showing here is that constants, non-zero constants, can be multipliers out in front of the determinant. They can factor out. All right, theorem 3.4 is about the conditions that yield a zero determinant. So we are going to again have A be an n by n square matrix, and any one of the properties is true. If that's true, then the determinant is zero. So these are all equal conditions that yield a zero determinant. So condition A says an entire row or an entire column consists of zeros. And if you think about our expansion by cofactors that we saw in chapter 3.1, that makes sense because a zero in a whole row or a whole column is going to zero everything out when we expand by the cofactors. Condition B that yields a zero determinant is that two rows or two columns are equal. And if you think about that, you could cancel them out. Right? We could use row operations and cancel those out, and we'll see why. And then condition C is that one row is a multiple of another row, or one column is a multiple of another column. So again, you see how you could cancel those out just by using the non-zero constant multiplication through. All right, let's look at proofs for these. So we're going to start with the proof of 3.3a that said that when B is obtained from A by swapping two rows or two columns, and the determinant of B is negative determinant of A. So we're going to prove this by induction. So we'll start with the k equals 2 case here. And so if k equals 2, then we've got A and B as 2 by 2 matrices. And we know the determinant of B equals the product of the diagonals, A2112 minus A22 A11. And that's just the negative of the determinant of A if we look at those diagonals. All right, so we are going to assume that this theorem holds for all matrices of order K. And just to go back and make clear, I hope you all saw that determinant B was determinant A, but with the rows swapped. All right, so we're assuming that this theorem holds for all matrices of order K. Then we're going to let A be a matrix of order K plus 1, and B is going to be the matrix obtained by swapping 2 rows of matrix A. So to find determinant A and determinant B, expand any row other than the swapped rows. The respective cofactors are opposites because they came from the K by K matrices that have the 2 rows swapped. Thus, we see for the K plus 1th case, the determinant of B equals negative determinant of A. So we see by induction that part theorem 3.3a, that when B is obtained from A by swapping 2 rows or 2 columns, the determinant of B is the negative of the determinant of A. All right, let's take a look at proof of 3.4a. So this says that you get a determinant that's equal to 0 when the entire row or an entire column consists of 0. So suppose that row I of matrix A is all zeros, then if we expand that cofactor, we know the determinant of A is the coefficient times the cofactor here, sorry. So it's the determinant of A equals A I sub j, the coefficients times the cofactor, and those I sub j's are all zeros, so that's just gonna make 0 times all of our cofactors equals 0. All right, so now let's look at proving part B's of these theorems. So proof of 3.4b, 3.4b says that we get a 0 determinant if 2 rows or 2 columns are equal. So let B be the matrix obtained from A by swapping 2 identical rows of A. So then we know, okay, well, determinant of B equals negative determinant of A based on 3.3a that we just proved. But B equals A because we swapped 2 identical rows. So the determinant of A equals the negative determinant of A. And the only way that is true is if the determinant of A is 0. So that proves that if you have 2 rows or columns that are equal, then the determinant is going to be 0. And you can also visualize that of course, by row operations, you could cancel those out if they're equal. Okay, we're going to look now at the proof of theorem 3.3b that says that B is obtained from A by adding a multiple of one row of A to another row of A, then the determinants are still going to be equal. So suppose B is obtained from row A by adding C times row K to row I. So C is our constant here, and then we're going to multiply it by row K and add that to row I. So now we can say, well, what would happen if we expand by the cofactors in row I, which is what we're going to do down here. So note that the cofactors of the Cij here and here are going to be the same for matrices A and B, because the matrices are the same everywhere except for this row I. So then we can say the determinant of B is going to be the coefficients of B multiplied by the cofactors, and we can expand B out here to just be, oh, well, it's C, our constant, of row K times the columns, where J is the indices for the columns, plus the value or coefficient value for row I. All right, and then we know we can factor out constants, so we can pull the constant out here and say, well, this is our constant, because we can pull constants out of sums. We learned that in calculus, times a kj, where that is row K, and then we're indexing through all the columns J, and the cofactor Cij, where I goes through all the indices there as well, plus Aij, the coefficient for row I times the cofactor ij, again, where it's cycling through all the indices. All right, well, we know that this is just going to be c times 0 because this value here is 0 based on the fact that we did c times row k and then plus the determinant of a. So we just end up with the determinant of a. And that's because this part here, the sum of the AKJ's cofactors IJ's is the determinant of a matrix with two identical rows. Row K and row I are identical since we've taken out the constant. And that's from the theorem that we proved up here. All right, let's look at how we can visualize this. So if you think about it, you can say, oh, okay, I'm expanding row K with the constant times row K plus a I1 down here, and that is what replaced in row I. That replaced our old row I. And so then we can see, oh yeah, we pull this out, we get the K's here and the K's over here. That is this expansion here. And then we get c times 0 because we've got identical values here. See how every value here is an identical one, and then plus the determinant of a. So we're able to cancel out here. So that's a visual of this last line here that says the sum of a, kj, cij is a determinant of a matrix with two identical rows, row k and row I. So here's our identical rows right here that are going to cancel out and give us 0 there. So that's where this 0 here is coming from. All right, let's look at the proof of 3.3 part C, and we'll do it for rows, and you'll see, okay, we could do the same argument for columns, just reverse our indices. So theorem 3.3c says when B is obtained from A by multiplying of a row, or you could swap it out to a column of A, by a non-zero constant C, then the determinant of B equals C times the determinant of A. So here we are swapping out each entry Bij with the constant C times Aij, still multiplied by the cofactors Cij that are going to cycle through all the indices. And then we know by properties of sums from calculus, you can pull the constant C out front. And so that's just C times this here, which is the determinant of A. All right, 3.4c is the case that yields a 0 determinant. So we're told if one row is a multiple of another row, or one column is a multiple of another column, we're going to get a determinant 0. So suppose B is a matrix with two equal rows or two equal columns, and A is obtained from B by multiplying one of the rows or columns by some non-zero scalar C. So using 3.3c, which said that the determinant of B equals C times the determinant of A, then we get this true. So determinant of A equals C times the determinant of B. And then using 3.4b, that said, well, if you've got two equal rows or columns, you're going to get a determinant that's 0. So then, well, determinant of B is 0. So then C times 0 is just 0. So determinant of A is 0. All right, geometrically, we can visualize that down here. So you can think about the signed area of a parallelogram with edges from 0, 0 to x1, y1, and 0, 0 to x2, y2. So that gives us a parallelogram. And then our last point out here is, what would this be? This would be x1 plus x2, and the height looks like y2. Okay, so if you think about the area of this parallelogram, well, that's just the 2 by 2 matrix, x1, y1, x2, y2. And so you can think about, oh, that area has the same properties as this 2 by 2 matrix when you perform an elementary row operation. You can also visualize in 3D. So think about a 3D picture where we start from the origin and we go to x1, y1, z1, x2, y2, z2, and x3, y3, z3. So that's going to have the same properties as this 3 by 3 matrix when you perform the elementary row operations. So you can think about it in 3 dimensions as the volume. So if we swap rows in 2 dimensions, you can kind of visualize, okay, here's your thumb pointing towards x1, y1, and your first finger pointing towards x2, y2. If you change dimensions, now your thumb's pointing up here, and your finger's pointing along the opposite axis. So you can see, oh, here's where our sign change comes from when we swap rows in the matrix, because now you've visually on the graph swapped your reflection here, and so that's corresponding with the sign change when we do our area calculation. And then in 3D, you can try it with 3 fingers. You've got 1, 2, 3 corresponding with x1, y1, z1, x2, y2, z2, and x3, y3, z3. And then if you rotate through, so here we're swapping rows 1 and 2, you can see how the orientation changes with your hand. In physics class, sometimes we use these finger swaps to do calculations to help us think about, you know, which way things swap and go. So when we do the swap from row 1 and row 2, then the sign of the area or the volume changes, right? Because we're changing from what we call the right hand orientation over here, now what we think of as a left-hand orientation. So you can think about that rotation as a sign swap. Think about it as a reflection across the 3 dimensions here. And we know reflections correspond with sign changes. Okay, if you want to visualize adding the multiple of one row to another row like we did in Theorem 3.3b, we can see here's a sample where we take the half of the first row and add it to the second row. Then you can think about the area is unchanged. So think about, here's our parallelogram. And then if we move our points around, it's still the same area. You could pick up this part of the diagram here in yellow and just move it over here, and you've still got the same net area. You just kind of rotated your parallelogram here. And then if you want to think about adding a multiple of one row to another, you can see, oh, that just kind of stretches out our parallelogram. So here we take the top row and multiply by constant c, and you can see, oh yeah, that multiplies x1 and y1, so that stretches the parallelogram out. So the area is just c times bigger. So the area used to be a base times height, now it's c times base times height, or c times a, because multiplication is commutative. So it just stretches it by a factor of c, which is what we saw back in Theorem 3.3b that said when b is obtained from a by adding a multiple of one row of a to another row of a, or one column, then the determinants are equal, right? So think about that stretch by the constant. I think this should say also Theorem 3.3c, which says if we multiply by a non-zero constant, then our determinant of b equals c times the determinant of a. That's what we're seeing visually here. Okay, so let's take a look at an example. So here is our matrix. So we're going to start with, and it doesn't have any zero entries. So we are going to work towards getting some zero entries to make our expansion by cofactor easier. All right, so I'm going to do row 1 plus 2 times row 2 and replace that with row 1. So that gives me here a new row 1. And I did this to get a 0 here in the position row 1 entry 3. All right, now I'd like to get another 0. So I see if I do row 3 minus 4 times row 2, I can get a 0 here in row 3, entry 3. And so remember, when we expand by cofactors, now we just have to expand by this column here, and we can use the 1 here. And so that 1 is in position row 2, column 3. So our exponent is going to be 2 plus 3. So -1 to the 2 plus 3 is -1 to the 5th, or -1. So that's why we have a negative out here. And then our remaining entries that go into the cofactor matrix are row 1 entries 1 and 2, and row 3 entries 1 and 2. And so that gives us this determinant, 2x2 determinant, much easier to figure out. So we have our -1, and then from the diagonals we get 14 times -13, and from the other diagonal we get 11 times -22. And so that simplifies to be a 60, so we get -1 times 60, or -60. Now remember, we can also do determinants in SIMPy, so let's head over to SIMPy and just verify these calculations. So I'll call this matrix A. So my first row was 4, 3, -2. My second row was 5, 4, 1. And my third row was -2, 3, and 4. Close off my matrix here. Type A just to verify my matrix is a match for my original matrix before I did all the row operations. And now we can say DETA, and here's our result, -60. So what we did by hand matches up with what we found in SIMPy. So you can imagine, if you're coding some sort of computer program, you might say, oh, I'm going to tell my computer to do some row operations here on these matrices and get it in a form like we did with zeros. In this case, in column 3, we got 2 zeros. And then it's much easier to do a cofactor expansion. Okay, in the next section, we're going to see some properties of determinants that we can apply for our calculations.